Colloquium this semester. We're going to do shorter talks from junior faculty who are CAN field members with the goal of hopefully getting students to know some of the faculty members that might be your advisor, as well as to get other faculty members who've been here for a while to know who the junior people are.
Not next week, though.
First and third weeks.
Sorry.
Yep.
2 disjoint weeks throughout the semester we will do this. Sorry about that. So today we have Christina who will be up first. Then we have Jamol Pender. Then we have Dmitry Savransky. Great. So Christina, take it away.
Today I'll be telling you about tensor estimation, and before I start on that, I'm going to just start with a very brief motivation. So suppose you're designing a recommendation system for an e-commerce platform. You might think about what kind of data that you have in hand. So you might have features of the users, features of the products. These are features that are directly observed or inputted when the user kind of registers on the platform. But in addition, you also have a bunch of interaction data. So these are data that for example, here you might have for a particular user, the set of ratings this user has provided for products in the past. Or for a particular product, what are the ratings that a user, that the set of users have provided for this product. In addition to rating data, you also might have, for example, purchase history. So for a particular user, what are the items they've bought in the past? Or for a particular user, you might have browsing history, so items that the user has clicked on. And you can imagine representing each of these data, the interaction data in a matrix. So in this picture here, I've kind of representing the rows. Each row represents a user. Each column represents a product. And for a particular row and column, there is an entry there if there was a user actually provided a rating for that particular product. But what we might want to do with this data is to ask, say, given us this subset of data that we've observed, for a particular user and product pair that we haven't observed in the past, can we go about and predict what its rating would be? So in addition to rating data, of course we have the product purchase history. We also have the browsing history. And so you can think of each of these as multimodal data. So we have data that all represent users' preferences and their interactions with products, but in somewhat different ways. And so you can think of each of we're going to represent each of the modes of interactions within one matrix. And so now when we stack it up, the data is represented in a tensor. So you can think of a tensor as a higher order generalization of a matrix. So whereas a matrix is simply a 2-order tensor where each data point is indexed by a pair of indices. So say Mij, the indices I and j denote the row and the column of that data point. A 3-order tensor, you can visualize it as a cube where each data point is indexed by a triplet of indices denoting the row, the column, and the depth. And a general t-order tensor, you can visualize it if you can as a t-dimensional hypercube, where every data point is indexed by a t-dimensional vector in a tensor. And so in general, this task of estimation is going to be, there's going to be some underlying ground truth tensor that we want to estimate. We're going to observe noisy observations of it, and we want to recover the original one. So for example, so in matrix estimation, we would have a data matrix that where the data points are sparsely observed, so we only have a few entries observed, and each entry is also observed with noise. And again, what we want to do is, given this sparse set of observations, to actually predict what the underlying matrix is. And similarly, in tensor estimation, the same thing would go for tensor. So in order to actually do prediction, give guarantees on the kind of prediction we can do, we need to actually impose some kind of modeling assumptions. If we have no assumptions on the data, if these data points were actually completely generated at random, then there's not much hope we have for predicting the unobserved entries. And so the model we're going to be looking at in this talk is that of a latent variable model. So there's a couple pieces to the model that we're going to assume. First of all, we'll assume that each entry is observed independently with probability p. So this is kind of a uniform sampling model. I assume that my observations are kind of uniformly spread across all possible indices. Every coordinate is associated to some latent feature that is sampled IID from some underlying population distribution. So if my rows here represented users, think of these alpha. Each alpha 1, alpha 2 would represent the latent features of the user associated to that row. And these features, these alphas, betas, and gammas, think of it as representing all features relevant to how the user interacts with in the system. Beta, again, represents all features relevant to how the product is received. And we assume that these features are sampled from some population distribution. But these features are unknown because we'll assume they're unknown because there may be some information we observe about the users. For example, we observe their gender, their age, their location, but it's restrictive to assume that the observed features are fully descriptive. So in this way, we're going to say there's some hidden features that we might not know, but they're fully descriptive. And our noise model will be that my data entry MUVW is equal to some function f, evaluated over the latent variables alpha, beta, and gamma, plus some additive noise. So means 0 additive. And we'll impose additional assumption on this function f. So particularly, we'll assume that this function is low rank. So the function can be written as a sum of R rank 1 tensors. You can think of these functions, these Q functions, as your eigenfunctions, and the lambdas are your eigenfunctions. One thing I want to point out is that we'll assume this function f is unknown, and also the latent variables alpha, beta, and gamma are also unknown. So this representation is not unique. There may be many pairs of functions and representations that all define the same, all lead to the same distribution. But now the goal is, given a sparse subset of these data points MUVW, can I go about and estimate f hat, which I want to approximate the function f evaluated over these latent variables. And I want to be able to evaluate this over the entire.
Do you assume that R is known?
Yes, but it is, yes, I will assume R is known, and it will show up in a tuning parameter of the algorithm. So in some sense, it also can be tuned heuristically as well. But I'm going to present results that, but we analyze it for a particular choice that is dependent on the rank. All right, so I'm going to be looking at, there's many approaches to that we could take to tensor estimation. Today I really want to introduce you to one particular approach, which is similarity-based collaborative filtering. And there's a couple kind of very nice properties of this method. But to start off, it has the basic idea of collaborative filtering is actually based on kernel regression, or using kind of a nearest neighbor non-parametric approach. So suppose we have a regression task, and so in our regression task we have a bunch of data points that we observe of input-output pairs. And the inputs are these kind of covariate x, and the output is y, where it's a noisy observation of some function of x. And so if we want to actually predict this function f of x as some new covariate value x, something natural we might try is to approximate this function by locally weighting the data points according to their distance in the x space. So, for example, this might be my kernel function, and this kernel function puts high weight on points that are near to this point and low weight on points that are far. And so as a result, I get kind of a smooth estimate of this function. So that's what we would like to do for our kind of matrix estimation or tensor estimation task. But the problem is that in tensor estimation, we actually don't know the distance in the covariate space. So our covariate space here in tensor setting would be the latent variables alpha, beta, and gamma. And we observe some observations are functions of alpha, beta, and gamma, but we don't actually know what alpha, beta, and gamma are. So we don't know the distances in the covariate space. And so as a result, we actually need to estimate this distances or similarities from the data itself. And given these estimated similarities, then we simply just predict by averaging similar data points in a nearest neighbor style. So this kind of approach is widely used in industry and has many practical advantages. For example, it's very simple to understand. It's you can implement it within a distributed parallelized system. And furthermore, if you change data points, a few data points, to update the estimate is very simple. But in fact, the nice thing is that even though this method is so simple, almost naively simple, it actually has very nice theoretical guarantees too. In fact, we can show, in our analysis of this method, we can in fact show stronger theoretical guarantees in the sense that we can provide entry-wise error bounds, as opposed to many other methods kind of provide error bounds in aggregate. Okay, so the key question we have to answer for this to design this algorithm is how do we go about estimating these similarities and distances from the data? And one naive idea is I'm just going to estimate the similarities between coordinates u and v by looking at comparing the rows associated to u and v. So for example, I might, here in the data matrix, I might look at the rows associated to u and v, look for columns that are commonly observed or commonly rated by both users, and then compute something like average square difference. Another way to visualize what the estimator is doing is I can represent my matrix as a graph where every row and column is associated to a vertex in my graph, and I have an edge between a user-movie pair if there was a rating in the data matrix. And so comparing the columns for which both rows have an entry is the same thing as looking at the one-hot neighbors of these two vertices in the data graph and looking for overlaps in the one-hot neighbors of vertices u and v. Now, the problem with using this naive method to estimate similarities is that it requires a very dense observations. In fact, it requires dense observations in order to guarantee that there are overlaps in the one-hot neighborhoods of two vertices. And so this is actually too expensive in terms of sample complexity. So next we want to ask, how can we improve this? How can we actually estimate similarities with fewer samples? And the natural idea is, why don't I actually take this idea of comparing neighborhoods in the graph, but expand the size of my neighborhood? So instead of just looking at the one-hot neighborhood of Alice and Bob, I'm going to look at the two hot neighbors and the three hot neighbors. So here I've expanded to the movies that were rated by users that rated movies that Bob and Alice rated. And now I've expanded to a larger set here that actually has an overlap now. So now I expand this neighborhood, local neighborhood of Alice and Bob in the data graph to a large enough set so there is an overlap. Now given these overlap items, I can estimate, compare the similarities by comparing the product of ratings along the paths to common vertices. So from Alice to Sound of Music and Bob to Sound of Music. And roughly, you can show that this statistic it looks like you're just taking higher order powers of your data matrix. So if you look at the three hot neighborhood, you can roughly approximate it by the third power of the data matrix. One caveat is that we restrict ourselves to only you don't repeatedly visit vertices, so this is like a breadth first search tree. So that's the one difference from just taking powers of the matrix. And so roughly, if my matrix had an expected singular value decomposition of U sigma V transpose, then the three hot neighborhood would have roughly a singular, will be roughly represented by U sigma cube V transpose. So whereas comparing the direct neighbors initially was computing a quantity that looked like this, then comparing the depth L boundary neighborhoods of Alice and Bob computes instead a quantity like this. And the only difference you see is that the singular values are raised to the power L here as opposed to just 1. And so if L is a constant, then you're kind of measuring the same quantity but distorted by a constant factor, and it ends up not being a problem in terms of asymptotic. So you have to choose this depth L sufficiently large to guarantee an overlap, and you can use martingale concentration to prove that these neighborhood statistics are well behaved. And in some sense, actually this does directly translate to some equivalent notions of saying that the spectrum of these data matrices is also well behaved. So as a summary, the algorithm, say for matrices, is two parts. First, we learn the similarities of distance, and then second, we use these similarities to do a final prediction. So the naive idea was to estimate by comparing rows, and that you can picture it as comparing the one-hot neighborhoods of two vertices in the graph. And given these estimates, we can do nearest neighbor averaging to get a final prediction, and that kind of relies on some smoothness assumptions on the function. But because this was not sample efficient for sparse data sets, then we can extend this idea to say instead we're going to compare expanded depth neighborhoods of vertices U and V in the bipartite graph that is constructed from the sparsely powered matrix. Okay, so this is the kind of extension of this iterative collaborative filtering for matrices. Now for tensors, you can ask what's the right graph to construct from my tensor? Well, one naive approach is I could just take my tensor, flatten it to a matrix by laying each layer side by side. But and then I could just do the whole algorithm on this matrix. Unfortunately, this actually does not achieve the best sample complexity, as the algorithm needs to observe like a few observations for every row and column. And by flattening the matrix, you're actually losing information about the relationship of the columns to each other. So the modification is actually very simple. Instead, we're going to still flatten the tensor and use this flattened matrix to learn these similarities or distances between coordinates. But when we do the actual final prediction task, we're going to do this nearest neighbor averaging in the full tensor shape. And it turns out that this kind of slight modification is enough to actually, when we analyze the sample complexity of this algorithm, we can actually achieve results that are same as using spectral methods or even optimization, convex optimization as well. So the concept is very simple. In fact, what are the guarantees we can show? We can show that with high probability, the max error over all entries goes to 0 if the number of observations grows as this quantity. This is n to the minus t over 2 plus delta for any constant delta that's positive. T is the order of the tensor. And it turns out that this sample complexity nearly matches. So matches minus this delta. Matches a conjectured lower bound. This lower bound comes from the sum of squares hierarchy, and this conjectured lower bound is that no computationally efficient algorithm can produce an efficient estimator with fewer samples than n to the minus t over 2. And in fact, turns out that this threshold, n to the minus t over 2, is exactly the threshold you need for connectivity for that graph that we did. Yeah.
Are you assuming that the depth L goes to infinity? Or is it fixed?
So, okay. So because I assume this delta, there's some plus delta which is positive, then my L can be constant. It's going to be a function of this delta.
I see.
But if delta goes to 0, then L will go to. So if I look at n to the minus t over 2 log n, then your depth L will have to go.
They're better than infinity. Okay. Thanks.
So in some sense, the interesting thought is that because the sample complexity, in fact, directly matches this connectivity threshold for the data graph, that gives another explanation for where this conjectured lower bound could come from. And it also implies that any algorithm that kind of hinges on this data graph being connected is not going to be able to push past this. All right. So the proof kind of involves showing that these estimated distances concentrate. So that involves a martingale concentration result, looking at these local neighborhoods. And then subsequently, you also need to show that these nearest neighbor averaging with noisy distance estimates pay as well. Okay, so I think I almost have used up more than my time. So a couple of future directions include kind of relaxing some of the assumptions we made for the model, incorporating side information, also applications of this technique to other high-dimensional statistics problems like tensor PCA, learning mixture models, and then also taking these ideas of learning these latent similarities or geometry in the context of sequential decision making. So kind of been exploring a little bit into contextual multi-ambiguities and work here as well.
One super quick question while Jamol sets
How does computational complexity scale with L?
With L, the computational complexity.
Yeah.
So actually how L is chosen is that we have to grow these neighborhoods until the size of the boundary is let's say roughly square root n. And so if you just think, and the size of the boundary is roughly like also the number of edges because it grows exponentially.
Right.
So the most expensive part is computing these similarities for every pair of vertices. So that would be n squared vertices that you compute the overlap in the boundaries.
Right.
And, yeah. So that's how.
Thanks.
But you can kind of improve it a little bit by subsampling and do like of course customization.
Great. So for those who don't know me, my name is Jamol Pender, assistant professor in the ORIE department. So I'd like to talk a little bit about some of the work I've been doing actually with a few people, some who happen to be in the room. So this is Sophia Nabisky, who is a CAM PhD student. Richard is here, he's a professor in MAD, and Elizabeth actually was a CAM PhD student as well as a CAM postdoc here. So much of my research is in queuing theory, so if you've ever waited in a line, you have some experience with being in a queue. And actually much of this work that I'll present today was actually motivated from me traveling from Ithaca to New York City, where I encountered this sign, which is a sign that you'll see if you're going to go over the George Washington Bridge. And here it kind of says, okay, there's an upper level and a lower level, and it kind of tells you how long it may take you from going from one or using one of those different options. So I decided to sort of abstract this problem a bit, and sorry if you've seen the slide before, but I'll go through it again. So I decided to abstract this model a little bit. And so the idea is that we have kind of a queuing system that measures how many people, and think of how many people are going to take the lower level or upper level. And our arrival rate is lambda, and the rate at which people are serviced is at rate mu. So this would represent the number of people who kind of decide to take the upper level and or choose the lower level. What's kind of unique about this is that I decided to incorporate what is known as a choice model, which kind of represents people making kind of decisions about what they see. So imagine you see on the bridge either the queue length or some waiting time of how long it's going to take you to go across the bridge. And so what you might want to do is, if you see two signs, you're going to choose typically the one that's going to say it's going to take you the shortest amount of time. And so this kind of choice model reflects that kind of dynamic. What's unique about this is that I've also incorporated a constant which reflects that the information that you might get may be delayed in some way. And so I've been interested in studying kind of models where this information kind of delay is present. And we'll go through a couple different kinds of ways this information can be embedded into the model. So this is just sort of an n-dimensional generalization of that. So you could have n different queues. One example of this would be Disney World. You have a million different rides, and you're going to choose with some probability on which one you're going to go to next. So generally what happens in queuing theory is that we don't really know how to we don't really understand how to actually compute things about various complicated models. And so one thing that we generally do is we might scale our model in a particular way that allows us to get something tractable in the end. And so this is known as kind of a fluid model scaling, where I scale up the number of arrivals, and you can't see it here, but I also scale down the queue length by the same parameter. So what does that yield? It turns out that, here's kind of a pictorial view of that, is that if I scale up the number of arrivals and I sort of scale their size down a bit, it turns out that we get kind of a fluid model. And so fluid model means dynamical system. So that's kind of how the world of CAM kind of merges into this talk. So we scale up our system. You can think of thousands of people in Disney trying to go to different types of rides. And you know, we just, instead of thinking them as people, we think they are particles. And so we get this fluid model, and it turns out that there's a lot of math that I've sort of drew under the hood, but you scale this model, you actually converge to, in this particular case, is a delay differential equation. And why is this useful is that we now can kind of use the theory of dynamical systems to understand kind of the dynamics of our original queuing model. And so this gives us some information about how the dynamics of our original kind of stochastic model might behave. And generally, fluid models kind of describe kind of the mean kind of trajectory that you see in a particular kind of stochastic model. So here's an example. So I set the arrival rate to 10, the service rate to 1, and I set my sort of lag in information at 0.34. You see the queues kind of oscillating a bit, but eventually they fade out and they converge to 5, which means basically half the people go to one queue and half the people go to the other queue. So I change this information parameter to 0.4, and in fact, the oscillations actually this time don't dissipate. So they don't go away, and they're actually sustained for the entire time. And one could argue that this is not exactly what you want. So generally, you think you're going to the shortest queue, but you actually end up going to the longest queue, and you actually experience something that you don't want. And so we like to think about, like, how can I, one, where do these kind of, or when, what kind of delay parameters can I have so that I don't actually experience these kinds of dynamics? So I'm interested in sort of computing exactly when that happens. So answer, in this particular case, we can actually compute in the n-dimensional case when exactly does, it turns out this is a hot bifurcation, when does this hot bifurcation occur? And we actually have an explicit formula in terms of the queuing model parameters that kind of tells us when this phenomenon is going to happen. So this kind of splits our kind of model space into two regions, one where it's stable and one where it's unstable. And we use 0.34 and 0.4 the last time, and you'll see that exactly at that point it's around 0.36 is where this kind of hot bifurcation occurs. So there's another model that we can use. This is me at the airport in Tel Aviv. And so if you read the fine print of the sign, they tell you that they're using a moving average of 10 minutes to actually tell you the waiting time. And this was at the customs airport screening. And here we have kind of a version of the model where instead of using the queue length at a time delay, we actually average over sort of a moving average window. And so we actually analyze this model as well. And it turns out you also get oscillations in this model as well. One thing we actually have proved recently is that the hot bifurcation for the moving average model actually happens later than the ones of the model which I call kind of a constant delay model, which is actually an interesting phenomenon. But what's interesting about this particular model, it turns out that this is called a isola center hot bifurcation that occurs here. And what it tells us actually in the moving average is that at first, you actually do not have a, like if I pick this point here, I don't have a hot bifurcation at all. So my queues kind of are going to go to like sort of 1/2 more or less. And as I move the delay into this region, I will experience a hot bifurcation. and you'll start to see oscillations in the system. But as I continue to kind of move the delay, actually the oscillations will disappear in this model. And it turns out this is intimately related to some things in thin films, where you actually have this sort of stretching kind of phenomenon. And you get these little bubbles in your thin film if you stretch it kind of long enough. So there's lots of interesting kind of generalizations and things that we're working on in terms of generalizing kind of the theory for this, where our constant delay model can be kind of thought of as a delta function acting on kind of the Q length. Our moving average is just kind of an indicator about a window. And you can think of kind of an arbitrary number of like different weight functions, and they all kind of affect the system differently. And so we've been kind of actively researching various different weight functions just to kind of get a sense of what's going on. What's also interesting is that you can view these as random variables. So instead of thinking that your delay is a fixed number, you can think of it as a random variable. And so in this case, it's a constant. In this case, it's a uniform random variable. In this case, it's exponential. So you can think of this in kind of a random variable context as well. We've also done some research. So this is a student who's actually in ORIE, who's worked with me on some projects, and this is my other PhD student, Andrew, who's also in ORIE, and we've worked on this information update problem, which I will mention shortly. So we've actually scraped some data from Disney, and there they actually have an issue where they give out apps, or you can use your cell phone, and you can look at and see where are all the rides and what's kind of the time that you're going to have to wait in order for you to sort of get on that ride. And so people kind of use the app to kind of figure out, well, maybe I don't go to that ride because it's going to take too long. And so this is sort of analogous to using your choice model. It turns out that if you look at various rides next to one another, you actually do see these kind of oscillations in the waiting times that they report. And so we've seen this actually on a variety of rides. And it turns out Disney will be coming to visit us, I guess, in 2 weeks. Because, yeah, they're very interested in this, apparently. So, so you actually do see this kind of in data, and you actually do see this actually, a hospital in Canada got sued because their waiting times actually were oscillating, and people kind of looked at what the thing was reporting, and they actually measured their time in the line, and it was way off. And someone got sick in a hospital because of that. And there's a whole host of stories that I could tell you about these kinds of systems. And so we, in some sense, want to be able to get it right. So in a model that is slightly different from the other two is where a system might actually use an update. So instead of actually looking at a fixed time in the past, you now have an update to a system, some time passes, it updates again, and time passes. You can model this with a function which is called a sawtooth function. So it's fixed for some time, it updates, it's fixed for some time, it updates, etc. So same idea, we can kind of scale the system appropriately. As we send our parameter off to infinity, we get another dynamical system. This is not a delay differential equation, it's a functional differential equation. But what's interesting about this particular model is that we can actually relate some of this work to autoregressive time series. So this is just a picture of showing that the simulations that we actually did of the real queuing system actually match quite favorably with the actual dynamical systems. So I'm not kidding you in saying that if we send things off to infinity or if things are close to infinity, that you actually do get the same dynamics as the dynamical system that comes out. This is another picture of that. Same as before, we get these oscillations that occur. What's slightly different is that you see in this particular model, since we have these kind of constant updates, the actual dynamics of the system are a little bit more or less smooth than our previous system. And you can actually show that kind of rigorously. Here, they sort of start out with oscillations and they sort of vanish when delta is 0.4, but when we change it to 0.42, the oscillations occur again and they're sustained. And so once again, we are interested in kind of finding the formula of where these kind of hot bifurcations occur. So in this case, you can actually prove an exact formula of where these kind of hot bifurcations occur in this model, and this sort of gives us some insight on when we expect to get these oscillations and when we don't. So what's interesting is that you can connect this to time series. So it turns out that the stability of my dynamical system actually is connected to the stationarity of my time series. And how you can view that is that as you're moving from one update to another, you're kind of using the information from the past. So you can think of it as a discrete kind of update. And that functions exactly like kind of time series. So the dynamical system we get out can be sort of mapped to kind of autoregressive time series. And then the stationarity is sort of equivalent to kind of the stability of the model, which is very nice. But also it hurts us in some sense that it's really hard to prove the stationarity of time series when you have more than two kind of updates. But other than that, this is sort of a nice connection between the two. It turns out you can compare the constant delay model with the one that actually has updates, and the difference in where the hot bifurcations occur are actually not that far off. And we're now starting to think about if we can sort of actually prove what the difference is between these two things. So some open problems in research. Originally I used to work kind of on time varying queues. I still do, but we're interested in, well, if you change some of the parameters in the model to actually make those non-stationary, how does that affect kind of the system? We're also interested in stability for other weight functions. So one thing that we've started to work on is, can I give kind of a data-driven version of stability in the sense that, what if I only know a few moments about the sort of delay distribution? Can I give bounds on where I think my hot bifurcation occurs? And it seems like we have gotten pretty far in trying to understand that. There's also notions of pricing information. So can we price giving people information, and how does that work? What's also important is that Disney actually uses something called last to enter service, and that's a very nice kind of measure of how long you're going to wait in a particular system. And so we're interested now in kind of using delayed versions of that, because actually the updates that Disney kind of gives are not sort of in real time. And so, so we're interested in studying kind of the actual indicators that they use, and sort of get a picture of what's going on there. I will mention that recently we kind of published a paper on understanding kind of the amplitude of the oscillation. So we're not only interested in studying like when they occur, but we're also interested in studying how large are they and sort of what is the frequency. And so we've kind of published a recent paper in the Science Journal on studying the amplitude as well. So I will move it there. Yes, ma'am.
So is your, I'm curious, do your updates kind of project into the future? So if as I see that I've been oscillating, and instead of like, can my update then anticipate that I'm going to continue oscillating? And does that help or does that not?
So I didn't get a chance to put this paper on the slide, but we had a recent paper on arXiv, I don't know, a couple weeks ago, that talks about looking at the time derivative of the Q length and using that as a forecast. And it turns out we can, if we use enough information, we can kind of eliminate all the oscillations. And also, if you use too much information, you can induce larger ones. So there's a right balance kind of using kind of the time derivative to kind of peek into the future of it.
Right. Hello. My name is Dmitry Savransky. I'm an assistant professor in mechanical and aerospace engineering, and there I run the Space Imaging and Optical Systems Lab, which, and I am also a member of the Carl Sagan Institute. And I just wanted to take 1 second to tell you about the Carl Sagan Institute, because it's a cool thing that we have at Cornell that you may or may not know about. This is a massively multidisciplinary institute that is composed of people who are interested in searching for life in the universe, including here on Earth. There's still yet to be found. And so we have members from something like 14 departments across 4 colleges working on completely disparate problems that are all somehow associated with life. So we have engineers, and astrophysicists, and astrobiologists, and electrobiologists, and others who do things that I do not completely understand or understand at all. And so this is a cool thing that you can learn about and get involved in. My group, what we do, basically, we do a lot of different things, which is cool, but you can lump what we do into 3 basic categories. We build hardware, optical instrumentation, and we also run low-level experiments trying to understand the controllability of optical systems and the auditability of optical systems. And I'm also interested in wavefront sensing and control, trying to sense the complex electric field from after you've done a silly thing like taking an image of it and throw it out most of the information, so phase retrieval. We do logistics. We analyze and optimize missions, both ground-based astronomical surveys and future potential space-based missions. And we do a lot of data analysis, figuring out what to do with the various data sources that the instruments that we work on collect, and how to tease the most information out of it. So, like it says in the blog, all sorts of engineering problems associated with control optical systems and space missions, and in particular, my pet science case is the direct imaging of exoplanets, and that's what I want to talk to you about, because I think it's insanely cool. So, wow. Every year I need to make this animation look right, and every year I forget. But here's my cartoon of of a planetary system, right? 1 planet, 1 star in the middle, and you kind of see a planet there. So obviously this is, the orbit of the planet is a 3-dimensional structure in space, and we observe it effectively projected into the plane of the sky. We look up into the sky, and there's a plane, so it's a projection, but it's a 3-dimensional structure, which means the planet is moving around the star. And of course, the star and the planet are actually co-orbiting the common center of mass, so the star moves as well. So, lots of different ways to infer the presence of this planet. You can stare at the star, and if your observations are precise enough, you can notice that the star is jiggling around, minus some common motion, and that's called astrometry, and so you can tell that something is orbiting that way. The star is also moving back and forth along the radial line of sight if the orbit geometry is correct, and via the Doppler effect, of course, the star is therefore changing color, like you see in my little cartoon, and so that is called Doppler spectroscopy, or radial velocity. Or, if you're lucky, the orbit is in just such an orientation that the planet passes in front of the star and behind the star, and so you get characteristic dips if you are integrating the total flux from the system. And this is called, unsurprisingly, transit photometry. And finally, if you're really good, you can try to collect photons from the planet itself, which is that curve there. And that's what I want to do. I want to actually get photons either emitted or reflected by the planet. So why? Why imaging? Well, probably all heard various sensationalist news reporting, lots of exoplanets. Exoplanets everywhere, next door. They're habitable, they're not habitable, they're infernos, who knows. We know about a lot of exoplanets. We have over 4,000 confirmed detections. Vast majority of them, almost 70%, are from a single spacecraft, from the Kepler and then the follow-on K2 mission, which was a transit photometry mission. Here I got these things roughly color-coded and symbol-coded by the detection method, so you can see relatively few, only on the order of 30 or so direct imaging detections. Clearly, not the best technique. The key point here is that in this phase space of planet mass versus some major axis, the direct imaging detections live in a completely different region from other methods, which makes perfect sense. The indirect methods are biased towards multiple orbits worth of data and therefore biased towards shorter periods. Really hard to see dim planet next to bright stars, so the bias for imaging is the exact opposite, larger orbits. So this isn't a talk about saying how imaging is better than the other techniques, it's a talk about saying how we need all of the things. We really want to observe all of the systems that we know of using many different methods, which means that imaging actually has to catch up. You'll also notice that this part, where we live, is not filled in. We don't actually know of any true Earth twins yet. We're not there yet. And we think the best way of getting to here is direct imaging from space. And so that's what I waste my time on. The other thing is that photons are precious. The whole reason why we want to investigate these planets is that we want to learn about how planets form, maybe learn something about our own solar system, but basically learn how the universe works. And imaging makes it really easy to get spectra, versus the only other method that gives you spectra is transit photometry in multiple bands. This is from space, this is from the ground. And I would argue objectively these spectra have more detailed information. Just compare my eye, this is much higher SNR detections of spectral features than here. So that is the point of imaging. Okay, so what do? I'm gonna run out of time, right? Do lots of different things, but if you think about putting together a space mission and figuring out how to optimize it for science, you can think about a lot of different things. You can think about, well, you need to kind of model the prior, right, in order to get any kind of answers, and so we do a lot of that, but I'm not going to talk about that today. We need to figure out how we're going to decide how to structure our surveys, how to make decisions of what star to look at next and how long to look at it. And we do that via mission simulation, which I will talk about briefly. As I said, we also do interpretation, which I don't talk about. And finally, we can think about post-processing, which I'll try to save some time to be able to say a few words about. So we have adopted a technique of Monte Carlo mission simulation, where literally what we're trying to do is, this is the standard system that you flow. You write your requirements, you have a mission objective, you write your top-level science requirements, they flow down into functional requirements, which flow down into subsystem requirements in your actual spacecraft. Then you do the validation and verification process by which you design the subsystems, you integrate them, and then through tests you show that what you build matches what you actually set out to build. We want to add a third step to this, where we take the functional implementation of this on paper, on the computer rather, we simulate its performance, we vary certain design parameters, show the variation in the performance, preferably in terms of distributions, because we don't know what the true prior is, and then feed back to update requirements to get more science out of the mission. Really, most importantly, to not get zero science out of the mission. That's really the key. Early on, a lot of these curves did not taper out here. They all kind of ended here, 10% complete mission failure. So some progress made, assuming we can believe our models. Why Monte Carlo? Monte Carlo is like the worst way to solve anything, right? No brute force. We use this because, here's my favorite sentence in the world, this problem is a online prize collecting windowed dynamical traveling salesman problem. The specific scheduling problem of a space mission for exoplanet imaging. And in particular, there's a lot of dynamic constraints that it's really hard to analytically model in a statistical sense, right? And so the people who do this statistically, they just kind of really throw out those dynamic constraints. But those dynamic constraints are really important. The schedulability of this is incredibly important. What you're seeing here is just for a sample of stars and assumed planet orbit for your spacecraft, it's only allowed to look at a particular target within the white regions. The colored regions represent basically some other solar system object getting in the way, like the sun, the earth, and the moon. This happens to be at a Lagrange point where the sun, the earth, and the moon might get in the way in certain regions of the sky. And then it also has solar panel keep-out constraints. So the sun has to be in a very specific place where we don't have power, and if your spacecraft doesn't have power, it gets really cranky and dies. So we'll do it this way. And then for each observation, the fundamental question that we are trying to answer is, when should we give up? When should we stop trying to collect photons and admit that we're not going to see anything and move on to the next thing? Because it's all about time allocation. You have very, very finite time to do your science. And so every observation, every second is precious, right? And so what you're seeing here is we can, for an assumed instrument, right? We don't have to make any assumptions on the population. In this space of angular separation between planet and star and planet radius, we can calculate the probability of detecting a planet in a given grid region with a given instrument. And you can see what's happening here is I'm bumping up time logarithmically in days. And so here, the color scales are actually at unity, so you're bound to see giant things close into your inner working angle. Here, you're down to almost 0. And then at a certain point, you're getting very marginal gains in a lot of the space. Obviously, you're getting some gains, but some of it is saturated. So you have to make a decision as to whether you stop wasting your time. And you have to allocate this not just for one observation, but for all of the observations. And the outcome of any one given observation can cause you to reevaluate the rest of your mission plan. So hence the Monte Carlo. So that's what we do. We build tools to simulate these whole missions. This is a simulation of the W-FIRST chronographic instrument, which is a NASA mission currently in phase B, which is NASA speak for they're almost going to let us build it. If we pass preliminary design review next month, we're going to implementation. What you're seeing here is a very carefully scheduled accounting for not just our science, but other science that the observatory has to do because it has other science instruments. These teardrops are the occlusion zones of the sun, the earth, and the moon, kind of bumping up and down over the ecliptic. And then the dots, the blue dots, are simulated past observations, and then the colored dots, the color scale represents how much time is currently being allocated. And if you look to future observations, those targets. If you look really carefully, you'll see that they're actually changing sometimes and blinking in and out, because the software is reevaluating the plan based on a rational agent that we've tried to construct for the entirety of the mission, and then updating that plan every time we make an observation. Okay, and now for something completely different. Let's talk about post-processing, because that's interesting too. We have already gotten data from our ground-based instruments. Hopefully in the future we will get some data from our space-based instruments. How do we get the signal? Very, very weak signal. We're effectively constantly working in sub-SNR1 regimes, right? The signal is buried within noise that, despite our best efforts, is basically at the level of the signal. And so these are simulated data sets, but these are representative of what we see on the ground. What you're seeing here is residual halo from the uncorrected atmospheric dispersion, atmospheric turbulence, rather. We have an extreme adaptive optics system running, but it can only go so fast, in this case at a kilohertz, and the atmosphere beats us. So we have some uncorrected wind butterfly noise and other static features that I'm not going to get into, but hidden in there is a planet. Okay, so non-Gaussian distributed noise of approximately the same magnitude as the signal, and it's correlated and evolving at multiple different timescales. That's okay. We know how to solve this, right? It's a cocktail party problem. No? Okay. It's a blind source separation problem. Lots and lots of different ways of solving these things, okay? But for whatever reason, the astronomical community has just been hammering for the last decade on two methods, because they're simple, linear, and easy to understand. So a few years back, I pitched to NASA that we should probably spend some time thinking about the other subcategories, subclasses of blind source separation, and I got somebody to agree. And so grad student and I have been working on that ever since, in exploring all the other methods. And so really, it's all about exploiting the spatial and temporal diversity. Right? The way that we get these super weak signals out is that observing that the majority of the information content is unwanted. It's all quasi-static noise. And if we could model, on average, that quasi-static noise, we should be able to subtract that out. That's the classical argument. That's how it goes. So here's just a single exposure from a long exposure series that are our data sets. Here is summing in linear space over the whole series, and you see there's a very bright signal here that just pops out. If this projector was better, you could maybe squint and see a second here. And there's a third one there that you can't possibly see because it's sub-SNR1 in this representation. What we do is we use the data to model itself. Because we have many realizations of the noise, we can figure out what the average and the distribution are. So you unfold the data, as we've heard before, you know the matrix, just 2D. So each row here represents an image. You can see very strong correlations between rows because you're basically imaging the same scene. And then if you're doing this the simplest way possible, SVD, right, you do a least squares fit. To it, you have something here, your covariance models the noise distribution, you truncate the SVD inversion here, and you subtract it off, and what you subtract it off, multiply that template by your target image, and what remains is an estimated signal. You can get way more clever, right, and apply the Cohen-Love theorem and actually figure out an optimal compacting, information compacting basis for it, right? So you just, instead of operating directly on the covariance of the of the original image set, you operate on the eigendecomposition of the covariance of the image set, which gives you an optimally compacting basis. And again, the whole point here is that the lowest mode of this, the mode with the largest eigenvalue, contains the most information, but that information is all that quasi-static noise. It's the stuff that you don't care about. So then again, you can just subtract it off, and what's left is your incredibly weak signal that is in one of those lower eigenvalue nodes. And when you do this, suddenly things start popping out, all three of them, for example. So that's cool. This isn't mine, mostly. This has been done before. We're trying to do something else. We're trying to get at something that doesn't require you to subtract out the noise. We want to instead directly model the signal. Because there's lots, as you can imagine, there's lots and lots of problems of subtracting a big thing from a big thing and expecting to accurately model a small thing. That's bad. Computers do that. Mathematicians should also do that. So the most successful thing we've tried so far is common spatial pattern filtering, where instead of trying to maximize the variance of the data, we're trying to maximize the difference between two windows of the same data set. Right? Again, very well known in audio processing and medical imaging, never done before as far as I can tell in astronomical imaging. So that's cool. So skipping all the math, this is just been published in the Astronomical Journal by graduate student Jacob Shapiro. Thanks. You're going to have to take my word for it, but these are very clear, these are individual CSP modes, and there's very clear signatures of point sources. And all we have to do is teach our computer to pick out the proper modes to graph. But of course, the open question of all this processing must modify the signals somehow. We want scientifically accurate information. We don't want the biasing effects of it in post-processing, which means that we need to develop a forward model, which has been done for the other methods that I showed, in this paper and others, and we've done that as well. So the real contribution to this paper is that we have a very accurate linear forward model that predicts the biasing that occurs on the signal when you apply this form of post-processing. And so this one of these is simulated, one of these curves is the forward model, and they're basically right on top of each other. So we have incredibly strong predictive power, and it works. Here's an original scene where you can see nothing. We apply our algorithm, and out pops this beautiful 63 SNR detection of beta XOR speed. This is actual data. You're seeing photons, thermal photons emitted by a planet that's about 60 light years away, just in case that excites you. It does me. Yeah, I got no time, so I'm going to skip the rest of this. Instead, I would like to invite you all to, or more students, faculty come too. My group meetings are Wednesdays at 9 a.m. this semester, and that's at 4:31. Absolutely anybody is welcome. Not next Wednesday, but the week after next Wednesday, I'm actually going to be talking to my group about all the new projects that we're spinning up this semester. So you might want to come listen to that. And I think I'm on time. So thank you very much.